In the depths of space, where there are no horizons, road signs, or GPS networks, how can a spacecraft know exactly where it is and which direction it needs to travel? Even the smallest error, carried across many years, could cause it to miss a planet by thousands of kilometers. Welcome to Night Cosmos Sleep. On tonight's journey, we will gently explore how light, time, and distance signals can become a map across the universe. And now, let the spacecraft drift beyond familiar space, as the guidance systems that once helped it find its way begin to fade into the distance. The spacecraft continues through the near-perfect silence. Its engines are functioning normally, the solar panels remain steadily pointed toward the sun, and the thermal control system continues to protect its instruments from the cold of space. Beyond the window, countless stars appear sharply against the deep darkness, seeming unchanged even as the spacecraft travels at tremendous speed. Everything is working as expected, except for one small detail that has just vanished from the navigation display. The icon showing a connection to positioning satellites. No alarm sounds, and no red warning lights flood the control panel. There is only a quiet, empty space where the spacecraft once received its location data, as though an invisible thread connecting it to Earth has just been removed. The familiar satellite network is still orbiting the planet far behind, but the spacecraft has traveled too far to keep relying on it in the same way. From that moment on, determining its position is no longer an automatic and almost invisible process. There is no road beneath the spacecraft to follow, no sign ahead, and no horizon anywhere around it to separate sky from ground. If every screen inside the cabin were turned off, a person looking through the window would have great difficulty telling which way was forward or backward, or where up and down might be. The stars are so distant that they remain almost motionless to the eye, even after the spacecraft has traveled thousands of kilometers. In this setting, motion is real, yet nearly impossible for the senses to detect. On Earth, we have become accustomed to a phone finding its location within seconds. A small dot appears on a map, showing which street the user is standing on, how far away the destination is, and which direction the person is moving. That convenience can make GPS seem like an invisible layer of mapping that covers everything, but in reality, it works only because of a carefully constructed network of satellites surrounding Earth. When a spacecraft leaves that environment, it also leaves the region of space those familiar signals were designed to serve. GPS does not determine position by watching a phone from above. The satellites do not look down in search of every car, ship, or person moving across the surface. Instead, they continuously transmit radio signals containing information about their own positions and the exact times those signals left the satellites. A phone simply listens quietly for those messages, like someone standing in darkness and hearing several bells ringing from different places. Radio waves travel at the speed of light, so the time a signal takes to move from a satellite to a receiver can be used to estimate distance. If the signal arrives slightly later, the satellite is farther away. If it arrives sooner, the satellite is closer. But knowing the distance to only one satellite is not enough to determine a position, because countless points can lie at exactly the same distance from it. The receiver must listen to several satellites at once, gradually eliminating possibilities until a reasonable location begins to emerge. The signal from a second satellite narrows the region where the receiver could be, while a third reduces that region even further. A fourth satellite is usually needed to correct errors in the receiver's internal clock, which is not as stable as the atomic clocks aboard the satellites. By combining several signals, the system can calculate a three-dimensional position while also correcting the time kept by the device itself. The blue dot on the screen is therefore created not only from distance, but also from the geometry of the network and the ability to measure time with extraordinary precision. Time plays such an important role because light can travel nearly 300 kilometers in just 1,000th of a second. An error that seems extremely small on a clock can become a large error on a map, causing the device to believe it is somewhere else. GPS compensates for this by comparing signals from several satellites whose atomic clocks are synchronized and continuously monitored. In daily life, this complex process happens so quietly that the user sees only the final result, a small dot resting precisely on the correct road. However, this network was designed mainly for people and vehicles near Earth's surface. Its satellites travel along orbits chosen to provide strong coverage around the planet, and most of their radio energy is directed downward, rather than transmitted evenly in every direction through space. As a spacecraft moves farther away, the satellites are no longer spread widely across the sky around it. Instead, they gradually appear clustered near the direction of Earth. This change makes position calculations more difficult, even when the spacecraft can still detect a few very weak signals. To determine its position accurately, a receiver needs not only several satellites, but satellites appearing in sufficiently different directions. If every signal source lies near the same part of the sky, the measurements may reveal whether the spacecraft is closer to or farther from Earth, while providing far less certainty about its displacement in other directions. It is like standing in a room and knowing only the distances to several lamps placed close together along the same wall. Those numbers offer part of the answer, but they are not enough to establish a clear position within the entire room. The increasing distance also weakens the signals, because their radio energy must spread across a larger region of space. Highly sensitive receivers can sometimes make use of signals leaking beyond the main coverage area, and some spacecraft near Earth or the Moon can still benefit from GPS. Even so, this does not transform the system into a navigation network covering the entire solar system. There is no complete ring of GPS satellites around Mars, no evenly spaced beacons along the route to Jupiter, and the space between the stars does not come with a ready-made artificial map for passing spacecraft. When the satellite icon disappears, the spacecraft does not immediately become completely lost, because it still has many other sensors and sources of data. What changes is that it can no longer wait for a single system to provide a ready-made answer about its location. From this point forward, it must construct that answer for itself by combining light, motion, time, and extremely faint signals arriving from great distances. Before it can do that, however, it must clearly distinguish between questions that may seem similar, yet actually describe entirely different parts of the journey. The first question is which way the spacecraft is facing, or more precisely, its orientation in space. This information reveals where the nose is pointing, whether the antenna is aimed correctly toward Earth, which region of the sky the telescope is observing, and whether the solar panels are still receiving sunlight. The second question concerns position, where the spacecraft is located relative to a chosen reference point, such as Earth, the Sun, or the planet it is approaching. These two questions are connected, but they cannot be used in place of one another. A spacecraft may know that its nose is pointing precisely toward Vega while still having no idea whether it is near Earth, traveling toward Mars, or already beyond the orbit of Neptune. Vega is so distant that its apparent direction changes very little as the spacecraft moves within the solar system. It can serve as an excellent reference for determining how the spacecraft is oriented, but it does not easily reveal where the spacecraft is located on a map. In space, knowing where you are looking and knowing where you are two different problems, even though everyday experience often makes them feel like the same thing. The third question concerns velocity, which includes both speed and direction of motion. Two spacecraft may be close together and moving equally fast, but if one is heading toward Mars while the other is moving away from it, their futures will be entirely different. Position describes where a spacecraft is at a particular moment, while velocity describes how that position is changing. To predict where the spacecraft will appear tomorrow or many months from now, its computers need both pieces of information. The final question is time, the reference that connects every measurement into a journey that can be calculated. A planet does not remain at its current location waiting for the spacecraft to arrive, because it continues moving around the Sun throughout the voyage. Earth is moving as well. Signals take time to cross space, and the spacecraft itself continues drifting while data is being collected. For this reason, knowing where an object is without knowing when that information was valid is rarely enough for navigation. Orientation, position, velocity, and time form 4 layers of information that must be assembled together. A device may measure one layer extremely well while being almost unable to answer the other 3. An attitude sensor can determine which way the spacecraft is facing, but cannot locate it on its own, while a ranging signal may reveal how far the spacecraft is from Earth without showing clearly how far it lies to either side. Space navigation, therefore, does not depend on a single instrument that knows everything. It relies on many devices that continually check and supplement one another. The motion of a spacecraft also differs from the way we usually imagine vehicles moving on Earth. A car almost always points toward the direction in which it is traveling, and an airplane generally moves in the direction its body is facing. But after a spacecraft completes an engine burn, it can shut down its engines and continue coasting along its orbit without keeping its nose aligned with its motion. It may turn sideways to communicate with Earth, rotate its solar panels toward the sun, or aim its telescope at another region of the sky, all while continuing along the path established earlier. Rotating the spacecraft does not mean it has turned onto a new trajectory. To change its direction of travel, it must produce thrust that alters its velocity, even if the change is very small. Seen from a distance, the spacecraft may glide through space in one direction while its nose points somewhere entirely different. This is one reason why familiar intuition from Earth is no longer enough to explain how a vehicle moves through open space. Inside the cabin, that motion leaves almost no direct sensation. Once the engines are off, there is no wind pressing against the hull, no road vibrating beneath it, and no nearby objects rushing backward. The stars remain almost fixed in place, creating the impression that the spacecraft is standing still within a motionless picture. In reality, however, it carries the velocity given to it at launch, the original motion of Earth, and the changes created by every course correction made along the way. Because it cannot rely on sensation, the spacecraft must depend continuously on measurement and prediction. Its computers begin with the previously estimated position and velocity, then use models of gravity and records of engine activity to calculate where the spacecraft may appear after a certain amount of time. When sensors provide new data, the system compares those measurements with the prediction and adjusts the solution when necessary. The spacecraft's position is therefore not a number found once and then left unchanged, but a result that is continually updated throughout the journey. Every solution carries some degree of uncertainty, much like the blue dot on a phone map is surrounded by a small circle of possible error. In deep space, that region of uncertainty can grow to hundreds or thousands of kilometers, depending on how much time has passed since the last measurement and how accurate the sensors are. The goal of navigation is not to eliminate every error completely, because that is nearly impossible, but to understand how large the uncertainty has become and keep it within safe limits. A very small error in velocity or timing, if allowed to accumulate quietly over many months, could cause a spacecraft to miss a planet it has spent years trying to reach. Behind it, Earth has become only one bright point among countless others. The GPS satellites continue circling the planet, steadily transmitting timing signals towards cities, oceans, and narrow roads across the surface. The spacecraft, however, has left the region of space that network was designed to serve, and the satellite icon on its display will not return in the familiar way. From this point forward, it must find other reference points and use them to construct its own map within the darkness. Before it can determine exactly where it is, the spacecraft must know how its body is oriented, where its antenna is pointing, and which part of the sky its optical instruments are observing. In a place with no natural north or south, and no absolute up or down, it needs landmarks distant enough to appear almost unchanged and bright enough to be recognized. The first tool that helps it do this is not an entirely new invention, but something that guided sailors across the oceans thousands of years ago. In the depths of space, the spacecraft begins to find its direction by looking toward the stars. Long before humans placed the first satellites into orbit, the sky was already the greatest navigation tool ever known. A sailor standing on the deck of a ship in the middle of the ocean could follow the position of the sun during the day, observe Polaris after nightfall, and use the horizon as a reference for estimating direction. A spacecraft does something similar, but instead of human eyes and experience, it relies on an extremely sensitive camera and a catalog containing thousands of carefully measured stars. At sea, finding direction once depended on signs that were simple but dependable. The sun rises near the east, sets near the west, and changes its height according to the time of day and the season. In the northern hemisphere, Polaris lies close to the direction of Earth's rotational axis, so it remains nearly fixed while the rest of the sky appears to turn around it. By measuring the height of this star above the horizon, sailors could estimate their latitude, revealing how far north or south they were. Yet knowing latitude was still not enough to determine a complete position on the ocean. A ship might know that it lay along the same line of latitude as a familiar city, while still having no idea how far east or west it had traveled. The problem of longitude was much more difficult because it depended on time. Earth completes one rotation in roughly a day, so the difference between local time and the time at a fixed reference point can be translated into an eastward or westward displacement. Once sufficiently accurate marine clocks became available, sailors could preserve the time of a reference location even after spending many weeks at sea. They observed the moment when the sun reached its highest point at their current location, then compared it with the time kept by the clock. If local noon arrived earlier or later than it did at the reference point, the ship could determine whether it had traveled east or west. A reliable clock therefore did more than measure time. It opened another dimension on the map. Those methods still required a horizon, a visible sky, and tables prepared in advance. In space, a spacecraft has no flat ocean surface to serve as a reference, and there is no natural north that applies everywhere. Even so, the central principle remains unchanged. If the spacecraft knows exactly where reliable points of light should appear, it can compare the real sky with a stored map and determine how its body is oriented in space. The instrument that performs this task is called a star tracker. It can be imagined as a camera with only one purpose: to observe the sky and recognize patterns of stars. Unlike an ordinary camera, a star tracker does not need to produce beautiful images for people to view. It must measure the positions of points of light with great precision, determine the angular distances between them, and convert that information into an answer about the spacecraft's orientation. Stored within the instrument is a star catalog prepared in advance. This catalog contains the positions, brightness levels, and other necessary characteristics of stars suitable for navigation. When the camera photographs a region of the sky, the computer does not see only a collection of isolated points. It measures how those points are arranged, which stars lie near one another, and how large the angles between them are. The resulting pattern is then compared with known patterns in the catalog. 3 or 4 stars can form a fingerprint distinctive enough to identify an entire region of the sky. The angular distances between the stars remain nearly unchanged as the spacecraft rotates, just as the shape of a triangle stays the same no matter how a sheet of paper is turned. The computer can compare many different triangles or polygons until it finds a matching pattern. Once the stars have been identified, it can determine which direction the camera is facing and, from that, calculate how the spacecraft is oriented in 3-dimensional space. A star tracker does not always need to know in advance which region of the sky the spacecraft is roughly facing. In some operating modes, it can begin almost completely disoriented and solve the problem on its own by comparing visible star patterns with the entire catalog. This process is often described with the evocative phrase "lost in space" recognition. The instrument needs neither a horizon nor a signal from Earth. It only needs to see enough stars clearly to identify a reliable pattern. Once a solution is found, the computer can determine precisely how the spacecraft is rotated around 3 imaginary axes. It knows where the nose is pointing, which side of the spacecraft is facing the sun, and whether the antenna is aimed approximately toward Earth. This allows a telescope to be directed toward a very small target in the sky, solar panels to maintain a suitable angle to the sunlight, and sensitive instruments to avoid pointing toward sources that are too bright. The required precision can sometimes be difficult to imagine intuitively. A telescope must do more than point toward the correct constellation. It must keep its target within a very narrow region of the sensor. Even a slight error could allow the desired source of light to drift out of view or cause a high-gain antenna to lose its alignment with a receiving station on Earth. For this reason, star trackers are often combined with other systems that continually check the spacecraft's orientation and make extremely gentle corrections. On many space probes, star trackers work together with gyroscopes and sun sensors. A sun sensor reveals the direction of the nearest source of light and can help the spacecraft maintain a safe orientation if the primary system encounters a problem. Gyroscopes record short-term changes in orientation, while the star tracker provides an external reference that corrects the gradual drift that accumulates over time. Each instrument has its own strength, and reliability emerges when they check one another. Although a star tracker is highly effective at determining orientation, it does not directly reveal where the spacecraft is located. This is its most important limitation. The stars selected as references are often tens, hundreds, or thousands of light years away. When a spacecraft moves a few million kilometers within the solar system, the resulting change in the shapes of the constellations is usually so small that it is almost impossible to detect through a simple observation. A star tracker can be thought of as an almost perfect compass. It can tell the spacecraft that one side of its body is facing a particular region of the sky, but it cannot reveal where the spacecraft lies along its orbit. A person could hold a compass in the middle of Hanoi, on a distant island, or far out at sea, and the needle would still point north. The direction of the needle is extremely useful, but by itself, it cannot reveal the complete location of the person holding it. The same is true when a spacecraft points toward Vega. From near Earth, from the region around Mars, or from somewhere beyond the orbit of Jupiter, Vega still appears in nearly the same direction in the sky. A star tracker can confirm that the telescope is aimed correctly at the star, but it cannot easily distinguish whether the spacecraft is 1 million kilometers from Earth or hundreds of millions of kilometers away. To answer that question, the system needs additional measurements involving distance, velocity, and time. The apparent stability of the sky is both an advantage and a limitation. If the stars changed position too quickly whenever the spacecraft moved, they would not provide a stable reference frame for determining orientation. Yet because they are so distant and appear almost unchanged, they also offer few obvious clues about position. The sky is an excellent map for revealing how the spacecraft is rotated, but it is not yet a complete map showing where the spacecraft is located. Although the stars appear motionless to the naked eye, they are actually moving. Every star has its own velocity through the galaxy, and over sufficiently long periods, its position in the sky will change. A star catalog therefore cannot be treated as an image that remains unchanged forever. Models must account for the proper motion of the stars and update their expected positions over time, especially during missions lasting many years or even decades. The apparent position of a star also depends on the motion of the observer. When a spacecraft travels at high speed, the incoming direction of the light appears slightly tilted compared with what would be seen if the spacecraft were standing still. This effect is known as the aberration of light, and can be understood through the way raindrops seem to fall at an angle towards someone who is running, even though they appear to fall almost vertically to a person standing still. In precise measurements, this small shift must be taken into account so that the spacecraft does not mistake its own motion for movement of the star. Light also takes time to travel from a star to the camera. When observing a star hundreds of light years away, the spacecraft does not see it as it is now, but as it appeared when the light began its journey hundreds of years earlier. For most navigation tasks, this does not create major uncertainty because the apparent position has already been modeled in the catalog. Still, it reminds us that the sky used by the spacecraft as a reference is not an image of one shared moment, but a collection of light that began its journey at many different times. In addition to the true motion of the stars, the sensor must also contend with sources of interference much closer to the spacecraft. A high-energy particle can strike the detector and create a false point of light. Sunlight reflected from part of the spacecraft may spill into the lens. A bright planet or the moon may occasionally enter the field of view and affect the way the instrument recognizes a pattern. The computer must therefore do more than locate bright points. It must also reject signals that do not match the known catalog. A star tracker also needs a sufficiently calm interval to capture a clear image of the sky. If the spacecraft rotates too quickly, the stars no longer appear as small points but stretch into trails across the detector. The pattern then becomes difficult to recognize, much like a photograph blurred because the camera moved while the shutter was open. The system may shorten the exposure time or use additional data from gyroscopes, but if the motion becomes too rapid, the star tracker may temporarily lose the ability to provide an accurate solution. Bright light can also create periods when the sky becomes difficult to read. If the camera points too close to the sun, the bright Earth, or a reflective surface, faint stars may disappear beneath the scattered light. The spacecraft has not truly lost the stars, it simply cannot see them clearly enough to recognize them. The sensor must wait for a more favorable viewing angle or temporarily rely on other systems to maintain its understanding of orientation. Remarkably, a spacecraft can control its pointing direction with extraordinary precision while still carrying a positional uncertainty of hundreds or even thousands of kilometers. Its telescope may be aimed perfectly at a distant star, while the computer remains unsure of the spacecraft's exact location along its trajectory. This is not a contradiction, because direction and position are different quantities measured in different ways. The sky therefore acts like a map that tells the spacecraft how to turn itself. Its points of light create a stable reference frame, helping the antenna, solar panels, and scientific instruments remain correctly oriented. But to determine where it is along the path between planets, the spacecraft must also measure distance, track velocity, and compare changes over time. The stars provide direction, but they cannot complete the entire journey on their own. Throughout most of the flight, the star tracker will look outward at regular intervals, recognize patterns, and correct the spacecraft's orientation estimate. These measurements happen quietly, without creating any dramatic sight for an observer, yet they allow every instrument to continue operating in the correct direction. Each time a star is recognized, the spacecraft seems to renew its connection with a frame of reference far larger than itself. There will be moments, however, when the starlight is obscured, the camera is blinded by a bright source, or the spacecraft rotates so quickly that the points of light stretch into trails. During those intervals, the spacecraft cannot continuously look outside to confirm how it is turning. It needs a system capable of remembering every change, preserving the solution in darkness, and waiting until the stars become clearly visible again. That memory of motion is carried by the gyroscopes. Try closing your eyes in a dark room, taking 10 steps forward, turning right, and then walking 5 more steps. For the first few moments, you can still imagine where you are, because your body remembers the distance you have traveled and the direction you have just changed. But if you had to continue this way for many hours, unable to see the walls, touch anything, or receive any reminder of your starting position, small errors in every step would gradually accumulate. Eventually, the place where you believe you are standing could be completely different from your actual location. A spacecraft faces a similar problem whenever the stars temporarily disappear from its sensors. It cannot continuously look outside to check its orientation, because the camera may be blinded by bright light, the spacecraft may be rotating too quickly, or part of its structure may block the region of sky it needs to observe. During those intervals, the spacecraft must rely on its own memory of motion. It records every rotation and every tiny change in velocity, then uses that information to continue estimating which way it is facing and how it is drifting. Before relying on more complex instruments, the spacecraft can find a simpler reference point in the sky, the sunday. A sun sensor does not create a complete map or reveal the spacecraft's precise location, but it can determine the direction from which the strongest light is arriving. That seemingly simple information is extremely important, because the spacecraft must keep its solar panels facing the light, protect sensitive instruments from excessive heat, and know which side of its body lies in darkness. A sun sensor usually works in a very direct way. Light passes through a narrow opening or a simple optical system and falls onto detectors inside the instrument. From the position of the illuminated region on the detector, the computer can calculate the angle between the sensor and the sunday. Some instruments need only indicate the sun's general direction with moderate accuracy, while more refined sensors can measure smaller angles to help maintain a stable orientation. The importance of this sensor becomes clearest when the spacecraft encounters a problem. If the main computer loses its sense of direction or the star tracker stops functioning, the system can place the spacecraft into a pre-planned safe mode. In that state, the first goal is not to continue scientific observations or perform a complex maneuver, but simply to survive. The spacecraft tries to keep its solar panels pointed toward the sun, maintain a safe temperature, reduce power consumption, and aim its antenna toward a region where communication with Earth may still be possible. A sun sensor, however, provides only one direction. It can reveal whether the sun lies to the left, the right, or ahead, but it cannot fully describe how the spacecraft is rotating around all three axes in space. If you look at a single lamp, You may know whether you are facing toward it or away from it, yet still be unsure how far your body is tilted or how much you have rotated around your line of sight. To record all of these changes, the spacecraft needs gyroscopes. The name may bring to mind a spinning wheel, and the earliest mechanical gyroscopes truly worked that way. A rapidly spinning object tends to preserve the direction of its axis, allowing it to provide a relatively stable reference as the vehicle around it changes orientation. On modern spacecraft, many gyroscopes no longer use large spinning wheels, but instead rely on light, vibration, or extremely small structures. Although the technologies differ, their shared purpose is to measure the spacecraft's rate of rotation. A gyroscope does not necessarily state directly that the spacecraft's nose is pointing toward a particular star. Instead, it usually measures how quickly the spacecraft is rotating around each axis and in which direction. If the computer knows the initial orientation, it can accumulate each change over time to estimate the current orientation. A slight turn to the left is recorded, followed by a gentle tilt, and then a rotation in the opposite direction. Each individual change may be extremely small, but when connected in the correct sequence, they form a memory of how the spacecraft has moved. Over short periods, that memory can be remarkably reliable. When the star tracker temporarily loses sight of the sky, the gyroscopes can preserve a sufficiently accurate orientation estimate for the spacecraft to keep its antenna, telescope, or solar panels pointed where they need to be. When the stars become visible again, the system compares the direction measured directly by the star tracker with the direction remembered by the gyroscopes. If the two results differ slightly, the computer uses the sky as a reference to correct the drift that developed while no external observation was available. Gyroscopes help the spacecraft remember how it has rotated, while accelerometers record changes in its linear motion. When an engine fires, when a small force pushes against the spacecraft, or when its trajectory changes, an accelerometer can detect that change. The instrument does not necessarily measure the spacecraft's current speed. Instead, it measures how quickly that speed is changing. From this information, the computer can gradually reconstruct the velocity and then estimate the position. The process can be imagined as tracking a journey without being allowed to look outside. If you know that you began at rest and that the vehicle accelerated for a certain amount of time, you can estimate the speed it reached. If you also know how long that speed was maintained, you can estimate the distance traveled. A spacecraft's computer performs a similar process, but across 3 dimensions, with multiple sensor axes and intervals that may extend for millions of seconds. In mathematical terms, accumulating acceleration over time makes it possible to estimate velocity, while continuing to accumulate velocity allows position to be estimated. Without seeing a planet or receiving a signal from Earth every second, the spacecraft can still predict where it is going by tracking every change that has occurred since its starting point. This is the foundation of inertial navigation, a method that allows a vehicle to maintain an estimate of its motion using sensors located entirely within itself. The greatest advantage of inertial navigation is its independence. It does not need to wait for an external signal to arrive. It is not interrupted simply because Earth lies behind the Sun, and it does not depend on whether a camera can see enough stars. At every moment, the spacecraft can use data from its gyroscopes and accelerometers to keep updating its predicted orientation, velocity, and position. Over a short interval, the system acts like a highly accurate memory of every motion the spacecraft has experienced. But this memory is not perfect. Every sensor carries a tiny amount of bias, even when manufactured with extraordinary precision. An accelerometer may report that the spacecraft is experiencing an extremely weak acceleration, even when no meaningful force is actually acting in that direction. At first, the error may be too small to produce any noticeable effect for several seconds. But the computer does not know that the value is incorrect. It continues accumulating the measurement as though the spacecraft were truly accelerating. As the acceleration error is accumulated over time, it creates an error in velocity. That velocity error is then accumulated again to produce an error in position, causing the gap between the prediction and reality to grow more rapidly. A tiny false signal, sustained across millions of seconds, can lead the computer to believe that the spacecraft has drifted tens, hundreds, or even thousands of kilometers in the wrong direction. The system may continue displaying neat numbers calculated to many decimal places, but that appearance of precision does not guarantee that the result is close to the truth. Gyroscopes can drift in a similar way. A tiny bias in the measured rotation rate causes the computer to keep adding an angle that does not truly exist. Over a few minutes, the difference may be almost meaningless, but after many hours or days, the orientation estimate begins to separate from the spacecraft's real direction. The spacecraft may believe its antenna is aimed precisely at Earth, while the actual signal beam has shifted far enough away for communication to weaken or disappear entirely. These errors do not necessarily mean that the instruments are damaged. Temperature can slightly alter the behavior of a sensor. Radiation can affect electronic components, and small vibrations within the spacecraft's structure can create unwanted signals. Engineers try to measure these biases in advance, build correction models, and track how they change during operation. Even so, no model can completely remove every uncertainty from a journey lasting many years. The spacecraft itself is not a perfectly rigid and motionless object. Fuel inside its tanks can shift when the spacecraft rotates or when an engine fires, redistributing mass and producing small changes in orientation. Moving mechanisms, reaction wheels, or robotic arms can exchange angular momentum with the rest of the spacecraft. When one device turns in one direction, the spacecraft's body may rotate slightly in the opposite direction, requiring the control system to detect and compensate for the change. Even after the engines have shut down, the spacecraft remains subject to extremely weak forces from its surroundings. Sunlight has no rest mass, but photons carry momentum and exert a tiny pressure when they strike a surface. Near Earth, this force is difficult to notice on a large object, but in deep space and over many months, it can alter a trajectory enough that navigators must account for it. The direction and magnitude of the effect also depend on the spacecraft's surface area, reflectivity, and orientation. The spacecraft's surfaces may also release extremely small amounts of gas or vapor. Materials that absorbed gases while still on Earth can slowly release them in a vacuum, while heat from onboard equipment may cause certain molecules to escape from the surface. If this outgassing is not perfectly balanced in every direction, it creates a very slight thrust. No one inside the cabin could feel it, but over a long journey, it can still contribute to the predicted trajectory, drifting away from reality. Engine burns are never perfectly identical to the ideal values written into the plan. An engine commanded to operate for a certain length of time may produce slightly more or less thrust than expected, while the thrust direction may differ by a very small angle from the calculated axis. Each individual difference may remain within acceptable limits, but after many course corrections, the results still have to be measured again, so that the spacecraft does not carry a quietly accumulating error. Gravity also introduces uncertainties that are difficult to eliminate completely. The major planets are tracked with great precision, but small asteroids, moons, or uneven distributions of mass within a celestial body can still alter a trajectory in ways that differ slightly from predictions. When passing close to a planet or asteroid, even a small error in the gravity model can cause the spacecraft to fly at a different altitude than planned. These forces are not mysterious, but they are not always known with absolute precision. From time to time, tiny dust particles also strike the spacecraft at high speed. Most impacts do not produce any meaningful change, but they remind us that space is not completely empty. A small particle can transfer an extremely tiny amount of momentum or alter the surface of a sensor. Over long periods, many random effects of this kind add another layer of uncertainty that the navigation system must accept, rather than pretending the spacecraft is traveling through an environment that is perfectly clean and entirely predictable. What is remarkable is that these forces are far too weak for a person to feel, yet time can amplify their effects. A slight push that persists, or a small velocity error that is not corrected early, will gradually carry the spacecraft away from its intended path. In space, not every danger comes from a violent event. Sometimes, a journey changes simply because a tiny force continues acting for long enough. The spacecraft cannot recognize this on its own by looking only at its inertial data. If an accelerometer consistently reports an incorrect value, the computer may believe that the reading represents real motion. If a gyroscope drifts slowly, the the system continues adding each tiny angle with an appearance of perfect precision. Inertial sensors do not know when they are wrong because they have no external reference for comparison. They simply record what the instruments inside the spacecraft detect and build an increasingly long memory from those numbers. Over short periods, that memory is accurate enough to keep the spacecraft stable when the stars temporarily disappear. But if it is never checked, it gradually becomes distorted, like a story remembered after too many years. The earliest details may be almost correct, but each time another tiny error is added, the distance between memory and reality grows. Eventually, the spacecraft may still believe it is following the proper course, even though its true position has shifted significantly away from the predicted trajectory. For this reason, inertial navigation is not used as an isolated solution. It works best when alternated with measurements from outside the spacecraft. Star trackers correct the attitude drift of gyroscopes, images of planets help verify lines of sight, and radio signals from Earth provide information about distance and velocity. Each comparison is like the spacecraft opening its eyes in a dark room, seeing a landmark, and then correcting the map it has drawn from memory. That memory of motion remains essential because no external reference can be observed continuously at every moment. The spacecraft must be able to continue flying through short intervals without waiting for someone else to tell it where it is. But to keep that memory from gradually becoming a distorted story, it must regularly compare it with a reference that lies beyond itself. Throughout many decades of space exploration, the most important reference point has remained the place where the spacecraft began its journey. From enormous antennas on the ground, Earth transmits radio signals, waits for them to cross the distance, and listens as they return. Within those extremely faint echoes, humans can find distance, velocity, and clues revealing how far the spacecraft's memory has drifted from the truth. From a quiet desert on Earth, an enormous antenna slowly tilts toward the sky. It is not searching for an object bright enough to be seen with the naked eye, but aiming at an almost empty point where a small spacecraft is drifting between the planets. A narrow radio signal is transmitted, leaving the atmosphere and racing into space at the speed of light. Many minutes or even hours later, Earth receives an extremely faint echo of that same signal. The echo does not carry sound in the way a voice returns from a distant cliff. It is a sequence of radio waves that has crossed millions or billions of kilometers, reached equipment aboard the spacecraft, and then been sent back. By analyzing how long the signal traveled, how its frequency changed, and where it appeared in the sky, navigators can estimate the spacecraft's distance, velocity, and part of its position. Without ever seeing the spacecraft itself, Earth can still trace its motion. The system responsible for much of NASA's long-distance communication is known as the Deep Space Network. It is not a single antenna, but an international network of large transmitting and receiving dishes located at 3 sites around the world: Goldstone in California, a complex near Madrid, and another near Canberra. These 3 locations are separated by roughly 1/3 of Earth's circumference, allowing one station to take over tracking before the spacecraft disappears below the horizon of another as the planet rotates. This arrangement allows Earth to maintain communication with spacecraft traveling in many different directions across the solar system. An antenna in California may track a spacecraft for several hours, but eventually Earth's rotation carries the target lower toward the horizon. As the signal begins to leave the station's field of view, another complex in Spain or Australia can start aiming toward the same region of the sky. The conversation is passed from one location to another while Earth continues to turn. These enormous dishes are not built only to transmit powerful signals. They must also listen for signals so weak that they are almost completely buried beneath the natural radio noise of the universe and the electronic noise of the equipment itself. The antenna gathers energy from a very narrow region of the sky, much like a large mirror concentrating light into a single point. Extremely sensitive amplifiers then raise the signal to a level where computers can separate it from the noise, even when the source is only a small spacecraft far from Earth. The first thing a radio echo can reveal is distance. A ground station sends a carefully encoded signal toward the spacecraft. The transponder aboard the spacecraft receives it, preserves its timing structure, and sends it back to Earth. By knowing exactly when the signal left the station and when it returned, navigators can calculate the total round-trip travel time. Because radio waves move at the speed of light, that time becomes a measuring tape stretched across space. If the signal takes longer than expected to return, the spacecraft may be farther away. If it comes back sooner, the distance may be smaller. During routine operations, deep space network ranging measurements can achieve an accuracy of about 1 meter, an extraordinary result after the signal has crossed interplanetary distances. That precision does not come from a single measurement, but from stable clocks, carefully designed signal codes, propagation models, and many layers of correction performed on the ground. The measurement, however, is not as simple as multiplying travel time by the speed of light. The signal must pass through Earth's ionosphere and atmosphere, where electron density, water vapor, and air pressure can alter the travel time by a very small amount. When the signal path passes close to the sun, plasma in the solar wind can also delay or distort it. These effects are slight, but when the goal is highly precise ranging, they cannot be ignored. The exact position of the receiving station on Earth must also be known. While the signal travels to the spacecraft and back, Earth continues rotating and moving along its orbit around the Sunday. The antenna is no longer in exactly the same place it occupied when the signal began its journey, so every calculation must be tied to a consistent timeline. Even small changes in the station's position, geological effects, or clock errors must be modeled before the final distance is accepted. A range measurement reveals how far the spacecraft is from Earth, but it does not fully describe how the spacecraft is moving. To determine velocity, navigators observe an extremely small change in radio frequency. As the spacecraft approaches, the wave crests arrive at Earth closer together, increasing the received frequency. As the spacecraft moves away, the crests spread farther apart and the frequency decreases. This is the Doppler effect, the same reason a vehicle's horn sounds higher as it approaches and lower after it passes. In space communication, this shift is not heard by the human ear, but measured with exceptionally stable instruments. The ground station knows the frequency it transmitted and can compare it with the frequency returned by the spacecraft. Even a very small change reveals how quickly the spacecraft is approaching or receding from Earth. The Deep Space Network can often measure the component of velocity along the line of sight with an accuracy of a fraction of a millimeter per second. That precision becomes easier to appreciate when we imagine a motion slower than the fingertips could sense. The spacecraft may be traveling at tens of thousands of kilometers per hour, yet the system can still detect an extremely small difference in its velocity toward Earth. Over many hours of tracking, the sequence of Doppler measurements reveals how the motion is changing, helping navigators determine whether gravity, engine activity, and subtle disturbances are keeping the spacecraft on its intended path. Doppler measurements, however, are most sensitive to motion along the line connecting the station and the spacecraft. If the spacecraft moves directly toward Earth or directly away from it, the frequency shift is clear. But if it travels mainly sideways across the sky, its distance from the station may change very little, making Doppler less effective at describing the complete motion. It is similar to watching a distant car. It is easier to tell whether it is approaching or moving away than to measure precisely how far it is sliding sideways. Range and Doppler therefore provide only part of the solution. A spacecraft could lie anywhere along a curved surface of equal distance from Earth, while the velocity measurement mainly reveals how quickly that distance is changing. To determine the full three-dimensional position, navigators must also know where the spacecraft lies in the sky, which means measuring the angular position of its signal relative to a stable reference frame. This is more difficult than it may seem, because simply pointing an antenna toward the spacecraft is not precise enough for interplanetary navigation. A large dish can receive a signal from a very narrow region of the sky, but even that narrow region is wider than what is needed to determine exactly how far the spacecraft lies to the left, right, above, or below its predicted trajectory. For this reason, the Deep Space Network uses widely separated stations and compares the times at which the signal reaches each one. If two people stand far apart and look at the same distant object, their viewing directions will differ slightly. That tiny difference contains information about the object's position. In radio measurements, stations in different parts of the world can observe the same signal from the spacecraft. Because they are separated by thousands of kilometers, the radio wave does not reach both stations at exactly the same moment. The extremely small difference in arrival time is measured and converted into information about the spacecraft's angle in the sky. The clocks at the two stations, the atmospheres above them, and the electronic equipment at each site can all introduce errors. To remove much of this uncertainty, a technique called delta Dor observes not only the spacecraft but also a natural radio source located nearby in the sky. The reference source is usually a very distant quasar, where matter surrounding a supermassive black hole releases so much energy that its radio signal can be detected from billions of light-years away. Because a quasar is so distant that its apparent position remains nearly fixed, it becomes a landmark against the background of the sky. The stations alternately measure the signals from the spacecraft and the quasar, then compare the differences in arrival time. Errors shared by the clocks, equipment, and transmission environment can be reduced, leaving a more precise measurement of the spacecraft's angular position relative to the reference source. This technique determines direction in the sky far more accurately than relying only on the pointing angle of the antenna. There is something remarkable about a quasar billions of light-years from Earth helping to guide a spacecraft traveling toward Mars or Jupiter. Its radio light began its journey long before humans existed, yet when it finally reaches Earth, it becomes a reference line for measuring the position of a small machine within the solar system. Sometimes, the most distant objects provide the most stable landmarks. When range, Doppler, and angular position are combined, navigators can construct a better three-dimensional solution. They know not only how far the spacecraft is from Earth, but also where it lies in the sky and how its line-of-sight velocity is changing. These measurements are entered into orbital models, compared with predictions, and then used to refine the estimates of the spacecraft's position, velocity, and region of uncertainty. If the solution shows that the spacecraft has drifted slightly off course, a trajectory correction maneuver can be planned. Small thrusters are fired for a few seconds or minutes, creating a tiny change in velocity that is nevertheless enough to alter where the spacecraft will arrive many months later. The Deep Space Network then continues listening to determine how closely the engine burn matched the plan. Each exchange forms a repeating cycle of prediction, measurement, and correction. These conversations, however, never take place in real time. When the spacecraft is far away, a signal may require many minutes or even hours to travel from Earth to its destination. If a response is needed, the signal must then make the entire journey back. During that interval, the spacecraft continues flying, the planets continue moving, and conditions aboard the spacecraft may have changed before humans receive the information. For this reason, the Deep Space Network does not control a spacecraft the way a driver steers a car with a wheel. Commands are usually calculated in advance, carefully checked, and then transmitted for the spacecraft to execute at a scheduled time. In situations requiring an immediate response, onboard systems must detect the problem and enter a safe state without waiting for Earth. The ground network provides guidance, data, and essential corrections, but distance always creates a delay that cannot be overcome. The network also serves far more than a single mission. Many probes, telescopes, and planetary spacecraft may need to use the large antennas during the same period. Tracking schedules must be allocated carefully, especially when a spacecraft is preparing to land, fly past a celestial body, or perform a critical maneuver. When demands overlap, mission teams may need to adjust their plans, store data on board, or wait for another transmission window. Signals can also become more difficult to interpret when the transmission path passes close to the Sunday plasma and the solar wind causes radio waves to fluctuate, adding uncertainty to range and frequency measurements. Earth's atmosphere, weather above the tracking station, and radio interference from the surrounding environment can also affect communication quality. Correction systems can reduce these effects, but they remind us that even a signal traveling through vacuum for most of its journey must still pass through layers of space that are not entirely quiet. The geometry between Earth and the spacecraft also determines which measurements are most useful. At some times, Doppler data describes velocity extremely well but does little to reduce uncertainty in the sideways direction. At other times, angular measurements from widely separated stations provide more valuable information. Navigators do not depend on a single type of data. They select and combine different measurements according to the positions of Earth, the spacecraft, the Sun, and the destination it is approaching. Despite these limitations, radio echoes remain among the most precise tools humans possess for tracking spacecraft in deep space. A ground station does not need to see the spacecraft against the sky or know how brightly it is shining. It only needs to detect an extremely faint carrier wave, measure when the signal returns, and recognize a tiny change in its rhythm. From those delicate traces, a trajectory stretching across millions of kilometers gradually comes into view. Far away, the spacecraft receives the signal from Earth and sends it back. Between its two encounters with the ground antenna, the signal has crossed a vast region of the solar system. It carries traces of the distance, motion, and environment through which it has traveled. Each returning signal is like another thread added to the invisible map that humans are constructing around the spacecraft. Distance in space is not measured with a ruler extending from Earth to another planet. It is measured by the time light takes to leave one place, reach another, and return. If the clock is wrong by even a very small amount, that invisible ruler can appear longer or shorter than it truly is. As journeys extend farther and the need for autonomy grows, the clock is no longer merely an instrument that tells time. It becomes part of the navigation system itself. Light can travel nearly 300 meters in just 1/1,000,000th of a second. That interval is far too brief for a person to perceive. But to a navigation system measuring distance with radio signals, it already represents the length of several buildings placed end to end. If the clock aboard the spacecraft runs even slightly faster or slower than it should, the recorded arrival time of a signal will also be wrong, and that seemingly invisible error can become hundreds of meters on a map. In deep space, distance is usually not measured by seeing the entire path from the starting point to the destination. The spacecraft and the ground station exchange signals that travel at the speed of light, then use the signal's travel time to determine the distance between them. To calculate that distance accurately, the system must answer two questions. When did the signal leave the transmitter, and when did it reach the receiver? For this reason, the clock does not merely sit beside the navigation system. It becomes part of the measurement itself. Every clock requires some repeatable motion that can divide time into equal intervals. Pendulum clocks rely on the steady swing of a weight. Mechanical clocks use gears and springs, and electronic clocks commonly use a quartz crystal that vibrates when an electric current passes through it. By counting those oscillations, the device can track how much time has passed. Yet no practical physical mechanism is completely immune to the effects of temperature, material aging, voltage, and the surrounding environment. A quartz clock may be extremely accurate in everyday life, but interplanetary navigation demands far more. A small error accumulating over many days can gradually separate the time recorded aboard the spacecraft from the standard time maintained on Earth. When the system uses two clocks that are no longer synchronized to measure a signal's travel time, it may mistake clock error for a change in distance. The spacecraft may not have moved differently at all, yet the map constructed by the computer can still begin to drift. Atomic clocks were created to maintain a more stable rhythm by using the natural properties of atoms as a reference. They do not measure time through the decay of atoms, nor do they contain a stream of matter that steadily disappears with each passing second. Instead, they make use of a highly specific energy transition frequency. When an electromagnetic signal is tuned to that frequency, the atoms respond in a detectable way, allowing the system to correct the rhythm of the electronic components inside the clock. Each type of atom can be imagined as a natural tuning fork with an exceptionally stable pitch. An ordinary tuning fork may change slightly as temperature or material structure shifts, but the transition frequency of an atom is far more consistent. The clock still uses electronic circuits and an oscillator to generate its rhythm, but the atoms continually act as inspectors. Whenever the electronic rhythm drifts away from the reference frequency, the system detects the difference and adjusts it back into alignment. This stability matters more than whether the clock is correct at a single moment. A clock may be set perfectly at departure, then begin gaining a small amount of time each day. Over a journey lasting months or years, that accumulated drift becomes the real danger. An atomic clock must keep the length of each second nearly unchanged across long periods. allowing a measurement made today to be compared with a signal transmitted many days earlier without carrying an ever-growing error. In the traditional navigation systems used by many deep space missions, the most accurate clocks remain at ground stations. Earth sends a time-tagged signal toward the spacecraft, which receives the signal and relays it back. The ground station measures the total time required for the signal to complete the two-way journey, then combines that result with Doppler data and orbital models to estimate the spacecraft's position and velocity. The method is reliable, but it requires Earth to participate in the entire measurement cycle. When the spacecraft is nearby, the waiting time may not create a major obstacle, but as it travels farther away, the signal takes longer to arrive, then requires a similar amount of time to return. While the ground station waits for the echo, the spacecraft continues moving and conditions along the journey continue to change. The large antennas must also devote tracking time to each mission, because every two-way measurement requires a stable communication link between the station and the spacecraft. If the spacecraft carries an atomic clock stable enough for navigation, the measurement process can change. Earth transmits a signal containing its departure time, and the spacecraft uses its own clock to record when the signal arrives. The difference between those two time markers allows the onboard computer to estimate the one-way travel time and therefore determine the distance without immediately sending the signal back and waiting for the ground station to complete the calculation. The spacecraft begins to generate its own navigation data, rather than receiving only results that have already been processed on Earth. This does not mean that the spacecraft completely ends its communication with the ground. Earth can still provide planetary positions, update orbital models, check the condition of onboard equipment, and send additional measurements. The difference is that the spacecraft no longer needs to depend on every round-trip signal cycle to determine how its distance is changing. During phases that require a rapid response, it can use a one-way signal and its onboard clock to update the navigation solution almost as soon as the data arrives. This capability is especially useful when a spacecraft is approaching a planet, preparing to enter orbit, or deciding when to fire its engines. If every calculation must wait for a signal to travel back to Earth and for a command to return, the information may already be outdated by the time the spacecraft uses it. A sufficiently stable clock does not make the signal travel faster, but it allows the spacecraft to use the information sooner. The physical distance remains, while dependence on two-way communication can be reduced. To test this idea, NASA developed the Deep Space Atomic Clock. The device used mercury ions confined by electromagnetic fields, limiting their contact with the walls of the chamber and reducing environmentally induced changes in frequency. The entire system was small enough to fly aboard a satellite instead of requiring the large atomic clock equipment normally installed at fixed ground stations. This was an important step toward moving an accurate time reference from Earth onto the vehicle in motion. The Deep Space Atomic Clock was launched into orbit on the 25th of June 2019 as a technology demonstration mission. Often described as being about the size of a toaster, the instrument was carried aboard a commercial satellite to test its ability to operate reliably for long periods in the space environment. The original mission was expected to last about 1 year, but it was later extended so the research team could continue monitoring its stability and collect additional data. By the 18th of September 2021, the mission had concluded successfully after more than 2 years of operation. The experiment showed that a compact atomic clock could maintain the stability required in space and support the development of more autonomous navigation systems. The Deep Space Atomic Clock did not directly guide a spacecraft to Mars during this mission, but it demonstrated that a precise timekeeping platform could be miniaturized and operated in orbit rather than existing only inside large facilities on the ground. In ground-based testing, the technology behind the Deep Space Atomic Clock was described as being up to about 50 times more stable than the atomic clocks used aboard GPS satellites. That level of stability would be equivalent to losing or gaining only about 1 second over millions of years if ideal conditions could be maintained. No one needs to wait that long and count every passing year to verify the result. The figure is simply a way of expressing an extremely small rate of drift measured over a much shorter period. Even so, an atomic clock cannot look outside and determine where the spacecraft is. It cannot identify which direction leads to Mars, measure where the nose of the spacecraft is pointing, or know how much thrust was produced by a recent engine burn. The clock only provides a time reference precise enough for other data to be interpreted correctly. It is like a ruler with exceptionally even markings, but it still requires something to measure and a clearly defined starting point. To turn time into distance, the spacecraft must still know where the signal was transmitted from, whether the transmission time was accurate, and how the source was moving. If the ground station's position is entered incorrectly, if the planet's orbital model is inaccurate, or if the wrong signal is identified, even a perfect clock can produce the wrong result. Precise timekeeping cannot correct every other error. It simply prevents the clock itself from becoming a major source of uncertainty in the measurement. The same is true of star trackers, accelerometers, and gyroscopes. Each instrument answers a different question, and the navigation system must assemble those answers into a complete solution. A star tracker reveals which way the spacecraft is facing, an accelerometer records changes in motion, radio signals carry information about distance and velocity, and the clock places all of that data in the correct sequence. Without accurate time, individual measurements may still be correct, yet become associated with the wrong moment. Imagine a spacecraft receiving information that its target planet is located at a certain position, while its clock is already several minutes off. During that interval, the planet has continued moving along its orbit, and the spacecraft is no longer where the computer believes it to be. If the system uses the outdated position to plan an engine burn, the error will not remain confined to the display. It may become an unsafe approach trajectory. Time is therefore not separate from space. It tells the system which moment belongs to each position. A stable clock also helps the spacecraft understand how much time has passed between measurements. When an accelerometer detects thrust, the computer must know how many seconds the force lasted in order to estimate the change in velocity. When a camera photographs a planet in two different positions against the stars, the system must know the interval between the images to calculate the apparent motion. When a radio pulse arrives earlier or later than expected, the clock determines how many kilometers that difference represents. In deep space, the question, "What time is it?" can therefore become remarkably similar to the question, "Where are we?" Time is not merely something that passes while the spacecraft completes its journey, nor is it used only to mark the departure date and expected arrival. It becomes one dimension of the map, linking signals, motion, and distance. Each tick of the clock forms another tiny marking on an invisible ruler stretched through the darkness between worlds. As long as communication with Earth remains available, the spacecraft can receive timing signals generated by atomic clocks on the ground. But that connection will not always exist. The sun may pass close to the line between Earth and the spacecraft, making radio communication difficult to use. The antenna may need to point elsewhere. Equipment may fail, or the distance may become so great that each message requires months or even years to arrive. On more distant journeys, the spacecraft will need sources of rhythm that do not depend entirely on a transmitter built by humans. Fortunately, the universe has created objects that emit repeating signals over long periods, like rotating lighthouses in the darkness. They are not satellites placed into orbit, nor were they designed to guide human travelers. Some are the collapsed cores left behind after the deaths of massive stars, spinning rapidly and sending regular pulses of radiation across the galaxy. For a spacecraft sensitive enough to listen, those distant rhythms could become natural clocks already placed throughout space. They do not provide an answer as simply as a GPS satellite does, but the amount by which each pulse arrives early or late can contain information about the observer's position. When signals from Earth are no longer the only point of reference, the spacecraft may begin navigating by counting the beats of dead stars. Far out in space are stars that have collapsed into spheres so dense that even a tiny amount of their material would carry an almost unimaginable mass. The remaining core of a massive star can contain more matter than the Sun, yet be compressed into a region only about as wide as a city. If it were squeezed any further, it could cross the final limit and become a black hole. But before reaching that threshold, it exists as a neutron star, one of the densest and strangest objects in the universe. Some neutron stars rotate only a few times per second, while the fastest can complete hundreds of rotations in that same interval. From regions near their magnetic poles, powerful beams of radiation are projected into space. The magnetic axis is usually not perfectly aligned with the rotational axis, so as the star spins, the beams sweep across wide circles, like the light of a lighthouse moving over a dark sea. If Earth or a spacecraft lies along that sweeping path, its instruments receive a pulse each time the beam passes. To an observer, the object appears to switch on and off continuously in a remarkably regular rhythm. Because of this behavior, such objects are called pulsars, a name derived from the idea of pulsing radio sources. The star does not actually stop emitting between pulses. Its beam has simply rotated away from the observer and returns after another complete turn. What we see is not a flashing lamp, but the regular trace of an object spinning in the darkness. Not every neutron star appears as a pulsar from our point of view. An object may produce beams of radiation, but if those beams never sweep across the observer's location, no pulses will be detected. Pulsars suitable for navigation must emit the right kind of signal, lie in favorable directions across the sky, and maintain a stable enough period for the arrival time of each pulse to be predicted. Among them, millisecond pulsars are especially valuable because they rotate extremely quickly and can preserve remarkably regular rhythms over long periods. Many millisecond pulsars were once accelerated by matter falling onto them from companion stars. Over long periods, this flow of material transferred additional angular momentum, causing the neutron star to spin faster and more steadily. After that process weakened or ended, the remaining object could continue rotating hundreds of times per second, with only tiny changes in its period. Their rhythms are stable enough that pulse arrival times can be predicted with great precision over many years, as long as the model is maintained and updated with new observations. That stability turns pulsars into natural clocks distributed throughout the galaxy. They were not built by humans. They do not fly in formation around Earth, and they do not transmit signals containing the receiver's coordinates. Instead, they send repeating pulses that a spacecraft can compare with a predicted schedule stored in its computer. The difference between the actual pulse and the expected pulse reveals part of the spacecraft's position, much like the delay of an echo can reveal how far the listener is standing from the source. To understand the principle, imagine a pulsar sending one wavefront after another across the solar system. If the spacecraft lies slightly closer to the pulsar along the direction of the source, each pulse travels a shorter distance before reaching the detector. The signal therefore arrives earlier than predicted at a chosen reference point. If the spacecraft lies farther away in the opposite direction, the path is longer and the pulses arrive later. That tiny difference in timing can be converted into a distance along the line of sight toward the pulsar. The spacecraft does not see each pulse as a bright flash in space. X-rays from distant pulsars are usually very faint, and the detector may receive only individual photons arriving at irregular intervals. The computer must record the exact moment each photon strikes the detector, then collect many photons over a sufficiently long observation period. When those arrival times are arranged according to the pulsar's predicted period, a faint rhythm gradually emerges from the data, like a distant drumbeat that becomes noticeable only after the listener patiently follows many beats in succession. X-rays are especially useful because these high-energy photons can be detected by relatively compact instruments in space and are not delayed by Earth's ionosphere in the way radio signals can be. However, Earth's atmosphere absorbs most cosmic X-rays, so telescopes designed to observe them must operate above the atmosphere. Aboard a spacecraft, an X-ray detector can point toward a pulsar, record each photon, and reconstruct a pulse pattern that the human eye could never see directly. The spacecraft's computer carries a model describing how quickly the pulsar should rotate, how its period is gradually slowing, and when each pulse should reach a chosen reference point. When the real signal is detected, the system compares the phase of the pulse with the model. If the pulse peak appears early or late, that difference becomes a measurement. However, the measurement is strongest along the line connecting the spacecraft and the pulsar, because it mainly reveals how far the spacecraft has moved toward or away from the source. A single pulsar, therefore, cannot immediately reveal a complete three-dimensional position. It is like a lighthouse that can indicate whether the spacecraft is nearer or farther along one particular direction, while leaving many possible positions in the other directions. By observing additional pulsars located in different parts of the sky, the spacecraft gains several independent measurement directions. These layers of information gradually intersect, narrowing the region where the spacecraft could be and producing an increasingly clear position solution. The onboard clock also plays a direct role in the calculation. If every pulse arrives later than predicted, the reason may not be that the spacecraft has moved, but that its clock is running incorrectly. With several pulsars in different directions, the computer can gradually separate position error from clock error. 3 spatial dimensions and the clock offset become quantities solved together, much like a GPS receiver usually needs signals from several satellites to determine its position while correcting its own internal clock. Even so, the comparison with GPS is valid only at the level of the general principle. GPS satellites are relatively close to Earth, transmit powerful signals, and include information designed specifically for navigation. Pulsars are hundreds or thousands of light years away, have no knowledge that the spacecraft exists, and emit radiation only through natural processes. A GPS receiver can detect several satellites almost simultaneously, while an X-ray telescope usually has to point toward pulsars, one at a time, and wait long enough to collect the required number of photons. The pulse rhythm also creates its own form of ambiguity. Because each pulse closely resembles the one that follows, the system needs a sufficiently accurate initial estimate to know which rotation of the pulsar it is comparing against. If the predicted position is too far off, the computer may mistake the difference for one or more complete cycles. Pulsar navigation, therefore, does not begin with a spacecraft that knows absolutely nothing about its location. It usually starts with an existing orbital solution, then uses the pulses to check that solution, narrow the uncertainty, and continue updating the journey. For many years, this capability existed only in models and laboratories, until NASA carried it to the International Space Station. The NICER telescope was installed outside the station to study neutron stars and X-rays, while also carrying a technology demonstration known as Sextant. Rather than requiring an entirely separate navigation instrument, Sextant used NICER's photon data and onboard software to test whether a moving vehicle could determine its own position using pulsars. During an experiment conducted in November 2017, the system selected 4 millisecond pulsars located in different regions of the sky. NICER pointed toward the targets one after another, collected their X-ray signals, and passed the photon arrival times to the Sextant algorithm. Over 2 days, the system generated 78 timing measurements and combined them autonomously into a position solution on the instrument's computer. The result was then compared with data from the GPS receiver aboard the International Space Station to determine how closely the pulsar-based solution matched the station's true position. The original goal was to locate NICER within a radius of about 10 miles or 16 kilometers, while the International Space Station raced around Earth at more than 17,500 miles per hour, nearly 28,000 kilometers per hour. Within roughly the first 8 hours, the solution converged within the desired accuracy region and remained below that limit for the rest of the experiment. A significant portion of the data even produced results within about 3 miles of the GPS position. The achievement was important not only because of the size of the error. The system performed the calculations automatically and in real time, while in orbit, rather than sending all the data back to Earth and waiting for specialists to reconstruct the position. This demonstrated that a rapidly moving vehicle could observe natural X-ray sources, compare them with stored models, and generate its own navigation solution. Sextant was not a complete system designed for an interstellar spacecraft, but it transformed a long-standing idea into a capability proven in space. Even so, there is still a considerable distance between a successful experiment and an instrument used routinely aboard spacecraft. X-ray pulsars are extremely faint, so accuracy depends on the telescope's collecting area and the length of the observation. A small detector may need to wait longer to gather enough photons, while a larger telescope requires more mass, electrical power, and space aboard the vehicle. Engineers must find a balance between the required sensitivity and the strict limitations of a practical mission. The spacecraft must also point the telescope accurately toward a pulsar while continuing to perform other tasks. The same attitude control system may need to keep the antenna aimed at Earth, the solar panels facing the Sun, or the camera directed toward the target planet. Time spent observing several pulsars must be included in the overall operating schedule, especially when each source needs to be monitored for a sufficiently long period. Pulsar navigation, therefore, does not operate like GPS, producing a new position every second. The pulse timing models must also be updated. Pulsars are highly stable, but they are not completely unchanging, because they gradually slow as they lose rotational energy. Some may experience sudden changes in their rotation rate, while pulsars in binary systems are affected by their motion around companion stars. Observatories on Earth can continue monitoring them and produce more accurate pulse schedules, which can then be transmitted to the spacecraft before or during its journey. The positions of the pulsars in the sky must also be known precisely, because any error in the source map will pass directly into the spacecraft's solution. A perfect clock and an extremely sensitive detector still cannot correct an incorrect reference coordinate. The system must also account for the spacecraft's motion, Earth's motion, and the way time measurements are converted to a common reference point within the solar system. These corrections are complex, but computers can prepare and perform them without turning every observation into a conversation with Earth. The required accuracy also changes from one phase of a mission to another. During a long journey between planets, knowing the position within a few kilometers or a few dozen kilometers may be enough to confirm that the spacecraft remains close to its predicted trajectory. But when preparing to pass near a small moon, travel through a narrow gap between rings, or land on a surface, the requirements may become far more demanding. In those situations, pulsar signals should work together with radio communication, cameras, and other sensors rather than replacing them entirely. A galactic GPS is therefore not a simple network that a spacecraft can switch on and immediately receive a perfect glowing dot on a map. It is a valuable method of autonomous navigation, especially during periods when regular communication with Earth is unavailable. It can check the trajectory, correct the onboard clock, and prevent inertial errors from continuing to grow in silence. But the best solution still comes from combining several types of measurements that support one another. Despite its limitations, the idea carries a remarkable beauty. GPS on Earth relies on satellites launched by humans and clocks built in laboratories. A spacecraft traveling farther away may find its direction through the dead cores of stars, objects formed by explosions that occurred long before humans learned to build the first clock. Those violent remnants have unintentionally become quiet time markers scattered throughout the galaxy. In the darkness of space, the spacecraft hears neither engines nor ocean waves. Its telescope slowly turns toward an almost invisible point, and the detector patiently records each X-ray photon. One photon arrives, followed by silence, and then another appears. When thousands of these tiny arrival times are placed together, an ancient rotational rhythm gradually emerges, revealing how far the spacecraft has moved through the darkness. Pulsars may help the spacecraft maintain a position solution that depends less heavily on Earth, but they are still far too distant to describe the object lying directly ahead in detail. As the spacecraft approaches a planet, a small moon, or a dark asteroid, the question is no longer simply where it is within the solar system. It must know where the target lies within the image, how quickly it is growing larger, and whether the approach path is carrying the spacecraft toward the correct destination. At that point, the neutron star lighthouses recede into the background as distant reference points. The spacecraft must turn its camera toward the world ahead, measure the outline gradually emerging from the darkness, and compare it with the maps stored on board. After learning to listen to the rhythms of dead stars, it will begin navigating with eyes of its own. For many weeks, the target is only a tiny point of light, almost impossible to distinguish from the countless stars behind it. The camera must take repeated images, align them, and search for the point that is moving slowly against the nearly motionless sky. Then, as the distance continues to narrow, that light begins to grow. A solitary point becomes a few pixels, then emerges as a small disk with one side illuminated and the other submerged in darkness. From the moment the first outline appears, the spacecraft is no longer aiming only toward coordinates calculated on Earth. It has begun to see the world it is approaching. The camera records the target's position in each frame, measures how far it lies from the expected direction, and tracks how the image changes over time. Every new picture is like the spacecraft opening its eyes, checking the path ahead, and correcting a prediction it has carried for many days. This method is called optical navigation because the guidance information is drawn from light. Instead of relying only on radio signals traveling between the spacecraft and Earth, the system uses cameras to observe a planet, moon, comet, or asteroid directly along the flight path. The camera may be built specifically for navigation, but on some missions, the same instrument is also used to collect scientific data. Images of the target help humans explore it, while also helping the spacecraft determine how accurately it is approaching. During the early phase, the target may be so small that it occupies only a single pixel. A point of light like this reveals nothing about the object's shape, surface, or rotation, but its position relative to the background stars already contains valuable information. The stars allow the computer to determine where the camera is pointing, while the target's location within the same frame creates a line of sight from the spacecraft to the celestial body. If the target appears slightly higher, lower, or farther to one side than predicted, the true trajectory may differ from the model. A single image mainly reveals the direction of the target, but it does not easily provide the complete distance. The spacecraft could be observing a small nearby object or a large distant one, and both might produce images of nearly the same size. Optical navigation therefore usually depends on a sequence of images taken at different times. By tracking how the line of sight changes, the computer can combine the visual data with the predicted motion of the spacecraft and the target to update the trajectories of both. The process can be imagined as watching a boat from the shore. A single glance tells us which direction the boat lies in, but not precisely how far it is from land. If we continue watching as we move along the coast, or as the boat changes position, the viewing direction shifts in a way that contains additional information about distance. In space, computers make these comparisons using extremely small angles, precise clocks, and orbital models calculated in advance. As the target draws closer and begins to appear as a distinct disk, its angular size provides another clue. If the true diameter of the planet or moon is known, a larger image usually means that the spacecraft is closer. The camera does not measure distance by extending a ruler into space. It measures how much of the field of view the object occupies. As a planet approaches, its outline expands across more pixels, and the distance estimate becomes more accurate. This is the principle used by the Orion spacecraft's optical navigation system. Its OpNav camera can photograph Earth and the Moon, then analyze their positions and sizes in the images to estimate direction and relative distance. The system was designed as a backup capability, giving Orion another way to determine its route home if communication with the ground were interrupted. During the Artemis 1 mission, the camera photographed Earth and the Moon at different phases and distances to evaluate how well the method worked under a range of conditions. The purpose of this backup system is not to replace every other form of navigation. Orion still relies on communication with ground networks and several internal sensors to track its motion. The optical camera provides an independent source of information, allowing the spacecraft to observe celestial bodies with known positions and compare them with its stored map. When several systems produce similar solutions, confidence increases. When they disagree, the difference becomes a sign that something needs to be examined. For missions traveling toward asteroids, cameras become even more important because the targets are usually small and their orbits may not be known as precisely as those of major planets. From Earth, astronomers measure an asteroid's position over many observations, but a tiny error in the sky can become hundreds of kilometers at the distance of the encounter. When the spacecraft photographs the target from a closer viewpoint, the new images help refine the prediction and determine more accurately where the two trajectories will intersect. NASA's Lucy spacecraft used its LOLORI camera to photograph the asteroid Donald Johanson during its approach in 2025. Over several weeks, the asteroid appeared increasingly bright against the stars, while each navigation image helped the mission team improve its predictions and confirm that the spacecraft was heading toward the chosen flyby point. Even though the positions of both Lucy and the asteroid were already known fairly well, the encounter still required great precision because Lucy passed the small target at approximately 13.4 kilometers per second. Importantly, the spacecraft does not fly directly toward the location where the asteroid appears in the current image. While it crosses the remaining distance, the target continues moving around the Sunday. A planet does not remain still and wait for a visitor from far away to arrive. The computer must predict the future positions of both objects and guide the spacecraft toward the meeting point, much like throwing a ball ahead of a running person instead of aiming at where that person was standing a moment earlier. If the journey lasts many months, aiming directly at the planet's current position would almost guarantee that the spacecraft arrived in empty space. By the time it reached the old coordinates, the planet would have traveled millions of kilometers farther along its orbit. Navigators therefore do not ask only where the target is now. They ask where it will be when the spacecraft arrives. Every new image helps them determine whether the predicted future encounter remains accurate. When the target is still very distant, a small change in trajectory may not immediately appear in an image. Over several days, however, the point of light will gradually drift away from its expected position if either the spacecraft or the celestial body is not moving according to the model. The computer can identify this trend before the error becomes too large and propose a small correction. A gentle push made early can change the final destination after millions of kilometers, while waiting until the last moment usually requires more fuel and leaves less time to recover. Although a camera creates the impression that the spacecraft is seeing reality directly, images can still be misleading. An asteroid is rarely a perfectly round sphere with a uniformly bright surface. It may be elongated, deeply hollowed, formed from two connected sections, or covered in regions that reflect light very differently. The brightest point in the image may therefore not lie at the center of mass, the point used to describe the object's true orbit. If the computer aims only at the brightest region, the line of sight may be offset from the physical center of the target. The illumination angle also changes the object's apparent position. When the sun lights only part of the surface, the camera may see a crescent rather than a complete disk. The center of the bright region is then shifted toward the illuminated side, while the object's true center remains closer to the boundary between light and shadow. The system must recognize the target's phase, shape, and rotation, so that it does not mistake a change in lighting for a change in trajectory. For a large, nearly spherical planet, the outline can be used to estimate the center fairly accurately. But with an irregular asteroid, each rotation may bring a different region of the surface into view, causing its shape and brightness to change continuously. An elongated object may appear brighter when its broad side faces the spacecraft and dimmer when its narrow end points toward the camera. Without accounting for this rotation, the computer may conclude that the target is changing distance or shifting across the background sky. A very dark target can also blend almost completely into the space behind it. An asteroid covered in dark material reflects very little sunlight, making it difficult to detect until the spacecraft has drawn considerably closer. The camera may need longer exposures or multiple combined images to strengthen the signal. But a long exposure can stretch points of light into trails if the spacecraft is moving. The system must balance collecting enough light with keeping the image sharp enough to measure position. Excessive brightness creates the opposite problem. If the camera points near the sun, scattered light inside the optical system can overwhelm faint targets. Dust around a comet, reflective particles near a planet, or light bouncing from part of the spacecraft may also create false streaks and points. The computer must distinguish the real target from stars, noise, and the trace of a high-energy particle passing through the detector. Even when the camera operates perfectly, the target's orbit may still contain uncertainty. Major planets are tracked with great precision, but small asteroids are often observed only over limited periods and may be affected by weak forces that have not been fully modeled. Sunlight, uneven thermal radiation from the surface, or a close encounter with another celestial body can alter the orbit slightly. The spacecraft therefore uses its images not only to determine its own position, but also to improve its understanding of where the target is truly heading. As the distance decreases, the nature of the navigation task gradually begins to change. During most of an interplanetary journey, the important question is where the spacecraft is relative to the Sun or Earth. But once the target occupies a significant part of the frame, the system becomes more concerned with the relative position between the spacecraft and the world ahead. The distance from Earth still matters for communication, but safety now depends on how high the spacecraft will pass above the planet, which side of the asteroid it will approach, or where it will touch down on the surface. This method is known as target relative navigation. The camera can track the horizon, craters, mountain ranges, or other known surface features and compare them with maps stored in the computer. If a crater appears farther to the left than expected, the spacecraft may be too far to the right along its approach path. If the horizon is growing faster than the model predicts, the distance may be closing more quickly than expected. Individual features on the surface begin to replace distant stars as navigation landmarks. Modern image analysis tools can use outlines, terrain, and apparent motion to estimate distance, construct three-dimensional models, and identify hazardous regions. Optical technology is being developed not only for spacecraft in flight, but also for landers, rovers, and astronauts operating on worlds without GPS. When a camera recognizes a crater, boulder, or horizon, those features become a natural system of landmarks across an unfamiliar surface. During the final phase of an approach, every new image can influence the next decision. At first, the target is only a point of light marked by a few pixels. Then it becomes an object with a visible phase, an outline, and rotational motion. As the spacecraft draws closer, the bright and dark regions on the surface begin to separate into plains, cliffs, craters, and large formations of rock. The region of uncertainty around the spacecraft's position also begins to contract. One image confirms the line of sight. The next shows whether the target is growing at the expected rate, and later images help determine the precise direction of approach. If the system detects an error, the engines can make a small adjustment to bring the flyby point back within the safe corridor. Each correction is like another stroke of a pen, making the path on the map narrower and clearer. Eventually, the spacecraft is no longer aiming toward a mathematical point in empty space. Ahead lies a real world with a horizon, a day side and a night side, and regions of terrain moving slowly across the frame. The camera continues measuring, the computer continues predicting, and each closer observation helps the spacecraft understand not only where the target is, but which part of that target is moving toward it. If the mission is a flyby, the system must ensure that the spacecraft passes at the correct distance, close enough for its scientific instruments to observe fine details while still avoiding a collision. If the mission is entering orbit, it must bring the spacecraft to the correct position and velocity for the gravity of the celestial body to capture it. If the mission is landing, the horizon will eventually disappear from the frame, replaced by a surface expanding rapidly below, while safe regions must be recognized before the final decision window closes. A camera creates a powerful sense of directness, as though simply seeing the target means the spacecraft knows everything with perfect accuracy. Yet every pixel still contains noise, every outline depends on illumination, and every orbital model carries uncertainty. Radio signals have their own errors, pulsar rhythms must be modeled, and optical sensors cannot reveal absolute truth in a single image. The most dangerous question is therefore not whether the spacecraft is wrong, because every measurement system is wrong to some degree. What matters is how large the error has become, which direction it is growing, and whether enough time remains to correct it. During an approach lasting several days, a small deviation may become clearly visible from one image to the next. But across a journey lasting many years, time itself can turn the smallest error into an enormous distance. After watching the target grow into an entire world within the frame, the spacecraft understands that seeing has never meant knowing with absolute precision. Each measurement narrows only part of the region of uncertainty, while the remainder continues traveling with it through space. And when a journey stretches from a few months into 10 years, the next question is no longer whether an error exists, but how far an almost invisible deviation today will carry the spacecraft from its target in the future. 1 millimeter per second is so small that it is almost impossible to notice. It is only about the thickness of a large grain of sand added to the spacecraft's motion with every passing second. But if its velocity is miscalculated by exactly 1 millimeter per second, and that error remains uncorrected for 10 years, the predicted position could differ from the true position by about 316 kilometers. If the error increases to 1 centimeter per second, that distance would exceed 3,100 kilometers. Those numbers still seem very small compared with the tens of thousands of kilometers per hour traveled by a spacecraft. Yet the danger does not lie in the initial size of the error. but in how long it is allowed to remain. Space gives a tiny deviation, millions of seconds, to keep pulling the spacecraft away from its predicted trajectory. Something almost invisible over a few minutes can grow larger than the length of many countries after several years. Velocity error is one of the easiest forms of error to accumulate. If the computer believes the spacecraft is moving slightly faster than it truly is, it will predict that the spacecraft travels farther with every passing second. The distance between the prediction and the actual position therefore grows almost continuously. The spacecraft does not need to make a sudden turn or suffer a violent collision. A small difference only needs to persist long enough for the map inside the computer to gradually separate from the journey unfolding beyond the window. This can happen after an engine burn that does not unfold exactly as planned. The engine may produce slightly less thrust, operate for a fraction of a second less than expected, or point at a tiny angle away from the calculated direction. Immediately after the maneuver, the difference may be almost impossible to recognize through a simple observation. But if the spacecraft continues flying for months before another measurement is made, that deviation has had enough time to alter the point through which its trajectory will pass. Angular error creates an effect that can be even more difficult to sense. Two lines may appear almost parallel at the beginning, but if extended far enough, the distance between them will continue to grow. An error of only 1 arcsecond, equal to 1/3600th of a degree, produces a sideways displacement of about 725 kilometers at a distance of 1 astronomical unit. 1 astronomical unit is close to the average distance between Earth and the Sun, so this scale still falls within the familiar range of interplanetary travel. 1 arcsecond is far too small for the human eye to distinguish easily. In the sky, it is only a tiny fraction of the Moon's apparent diameter. But if the direction of a trajectory is tilted by that amount and extended across hundreds of millions of kilometers, the final destination may shift far enough for the spacecraft to miss a planet, pass on the wrong side of a moon, or fail to enter the narrow corridor required for orbital insertion. Angular error does not necessarily mean that the spacecraft itself is pointing in the wrong direction. It may appear in the camera's line of sight, in the coordinates of the target, or in the way the computer interprets the position of a reference star. A sensor may be working almost perfectly, but if one landmark in the stored map contains a slight error, every direction constructed from that landmark will carry the error with it. As the distance increases, what was once a tiny difference begins to widen like two beams of light separating in the darkness. Time creates another kind of error, because in space, arriving at the correct location at the wrong moment can still mean missing the target. A planet does not remain fixed at one coordinate. It continually moves around the sundial. If the spacecraft reaches the orbital crossing point earlier than expected, the planet may not have arrived yet. If it arrives too late, the world may already have passed, leaving only empty space behind. This makes interplanetary navigation more like a meeting between two moving objects than a journey toward a fixed address. The spacecraft does not simply aim at where the planet appears in the sky. It must travel toward the position the planet will occupy in the future. Even a small error in the timing of an engine burn, the duration of the burn, or the rhythm of the onboard clock can change the moment of encounter. Arriving at the wrong time can therefore be just as dangerous as traveling in the wrong direction. Even when every sensor is operating correctly, the model used to predict the journey remains only an approximation of reality. The computer accounts for the gravity of the Sun, the planets, and other important bodies, but space is not perfectly simple. Solar radiation pressure, uneven thermal radiation from the spacecraft, the motion of fuel inside its tanks, and the gravity of smaller objects can all contribute to changes in the trajectory. Each factor is included in the model as accurately as possible, but no value is entirely free from uncertainty. The mass of an asteroid may not be known precisely. The true direction of thrust may be slightly different from the estimate, and the spacecraft's surface may reflect sunlight differently from what was originally assumed. Even an excellent model is not the universe itself. It is only the best approximation humans can construct from the measurements available. For this reason, navigators do not imagine the spacecraft as an absolute point lying on a perfectly thin line. Its position is understood as a region of probability, where some locations are more likely than others. This region may resemble an elongated ellipsoid or a curved tube surrounding the predicted trajectory. The spacecraft is most likely to be near the center, but there is still a chance that it lies off to one side. The shape of this uncertainty region depends on the types of measurements that have been used. Doppler data measures velocity along the line between Earth and the spacecraft extremely well, but it does not directly describe all sideways motion across the sky. Optical cameras can measure the line of sight toward a planet with great precision, but while the target is still distant and appears only as a point of light, determining the absolute distance may remain difficult. Each measurement causes the uncertainty region to contract in certain directions while leaving it extended in others. The spacecraft can be imagined as lying somewhere inside an invisible corridor. A range measurement shortens that corridor along the forward and backward direction, while a new image narrows it from side to side. Doppler data refines the component of velocity toward or away from Earth, while star trackers verify the spacecraft's orientation. No single measurement removes every doubt, but together they make the region of possible locations increasingly smaller. The uncertainty region also changes, even when no new measurements are available. As the spacecraft continues flying, small errors in velocity and the orbital model are projected forward, causing the region to expand. If communication with Earth is interrupted, or the camera cannot observe the target for several days, the solution does not immediately become useless, but confidence in it gradually decreases. The longer the spacecraft goes without seeing an external landmark, the less certain it becomes about where it truly is. That is why mid-course corrections are planned well in advance. The spacecraft does not wait until the target fills the frame before trying to correct every deviation that has accumulated. After receiving new data, navigators calculate where the current trajectory will carry the spacecraft and whether it still lies within the safe corridor. If necessary, small thrusters are fired to produce a very slight change in velocity. An early correction usually saves fuel because the remaining travel time amplifies the effect of a small push. A tiny change made today can shift the destination by hundreds of kilometers many months later. The spacecraft does not need to turn sharply toward the target like a car making a sudden turn on a road. It simply adjusts its velocity slightly and allows its natural motion to gradually carry the trajectory toward the desired point. If the correction is delayed for too long, the same deviation may require far more thrust. Once the planet is nearby, the spacecraft has very little time left to shift its flight path by a sufficient distance. A stronger engine burn consumes more fuel, places greater demands on the equipment, and may alter the observation plan. In a serious situation, the spacecraft may no longer be able to enter a safe orbit, forcing the mission to follow a different trajectory or accept that it will miss the target. These decisions are not postponed until navigators know with certainty that the spacecraft has gone off course. If they waited for absolute proof, the best opportunity to correct the problem might already have passed. Instead, they monitor probabilities, examine the direction in which the uncertainty region is expanding, and determine whether a significant part of it is moving beyond the safe corridor. The spacecraft is corrected when the risk becomes large enough, even though its true position can never be known completely. Navigation therefore becomes more like managing uncertainty than finding a single number. Every measurement contains error. Every model has limitations. And every engine burn unfolds slightly differently from the ideal plan. Navigators do not hide these realities behind a result that appears too perfect. They include uncertainty in the calculations, track how it changes, and choose the action most likely to keep the spacecraft safe. Errors can sometimes cancel one another for a while, making the journey appear more accurate than it truly is. A velocity error in one direction may be temporarily hidden by a different error in the gravity model. But that coincidence cannot be trusted for long. When conditions change, the two errors no longer cancel, and the trajectory may begin drifting rapidly in a way that was not previously visible. A new measurement may cause the estimated position to change suddenly, but that does not mean the spacecraft has just jumped to another location. What has changed is the system's understanding of where it is. Before the measurement, the spacecraft was already at its true position, but the computer did not know it precisely. Once new data arrives, the uncertainty region is reshaped, and the most probable point moves closer to reality. This distinction is important because the map does not control the universe. The spacecraft does not follow the line drawn on a screen simply because the computer believes in it. It follows gravity, inertia, and the real forces that have acted on its body. The model is only trying to keep pace with that motion. If the data is not good enough, the map can be wrong, even while the numbers on the display are shown with many decimal places. A long number is not necessarily a certain one. The computer may report the spacecraft's position to the nearest meter, while the true uncertainty region remains hundreds of kilometers wide because the available measurements have not narrowed it sufficiently. The detail of the display and the accuracy of the underlying knowledge are two different things. In space navigation, honesty about uncertainty matters more than creating an impression of absolute precision. Over 10 years, a tiny velocity error can carry the spacecraft hundreds or thousands of kilometers away from its predicted position. An angular deviation too small to notice can grow into a distance large enough to miss an entire world. A clock that runs only slightly slow may cause the spacecraft to arrive too late for its encounter, while an incomplete model can quietly direct the entire calculation along the wrong path. Yet the spacecraft is not powerless against these errors. It continually receives radio signals, observes the stars, watches its target, tracks its inertial motion, and compares all of this information with predictions. Each source of data is like a witness who has seen only part of what happened. No witness is perfectly accurate, but when their accounts are placed side by side, inconsistencies begin to emerge. A star tracker may reveal that a gyroscope has drifted. Doppler data may show that the true velocity does not match the result calculated from the accelerometers. A camera may detect that the planet lies away from the position predicted by the orbital model, while an atomic clock helps ensure that the measurements are not assigned to the wrong moments. The error of one system becomes easier to detect when examined by another system based on a different physical principle. The solution, then, is not to build a sensor that never makes a mistake. Such a device almost never exists in the real world, especially after years of operating amid radiation, changing temperatures, and enormous distances. A more reliable approach is to allow several independent measurements to build the solution together, continually checking whether they agree. Safety comes from detecting a deviation before it has time to grow too large. The spacecraft is not simply flying through empty space. It is moving through a region of uncertainty that constantly changes shape, contracting after each measurement and expanding as time continues to pass. A successful journey does not require absolute certainty about position at every moment. It requires understanding the uncertainty clearly enough to choose the next correction. When several sensors observe the same journey, the computer must decide which data is more trustworthy, which measurement is merely noise, and when a small difference truly indicates that the spacecraft is drifting off course. It cannot place complete faith in the camera, the gyroscopes, the radio signals, or the pulsars. It must learn to combine these imperfect accounts into a single picture, and that is the next step of the journey. It is not about finding one instrument that knows everything, but about building a system capable of recognizing when its own understanding is wrong. Among numbers that are never completely certain, the spacecraft must decide where it is. The star tracker indicates that the spacecraft is facing almost exactly the right direction. The gyroscope, however, reports that the body has drifted by a very small angle. The camera aimed at the planet finds the target slightly higher than predicted, while a radio signal from Earth suggests that the spacecraft's velocity is lower than the model expects. None of the instruments is completely silent, yet they are not telling the same story. At that moment, the computer cannot simply choose one sensor and ignore all the others. It must decide which differences are only noise, which come from ordinary drift, and which indicate that the spacecraft is truly moving away from its expected trajectory. If it places too much trust in an incorrect measurement, the system may guide itself off course. If it ignores a valid warning, the error may continue growing until there is no longer enough time to correct it. This is where navigation becomes a continuous process of judgment. The spacecraft does not possess a single instrument capable of looking outside and revealing the entire truth. It has many sensors, each observing only one part of the journey and carrying some degree of error. The computer must assemble those imperfect pieces of information into a unified solution accurate enough to determine where the spacecraft is and what it should do next. The process usually begins with a prediction. Starting from the position and velocity estimated at the previous moment, the computer uses gravitational models, the history of engine activity, and other known forces to calculate where the spacecraft is likely to appear several seconds or minutes later. If nothing unusual has happened, the new position should lie close to that prediction. This becomes the temporary map the system carries while waiting for more information from the outside world. The sensors then produce new measurements. The camera sees the planet at a particular location in the frame. The gyroscopes record rotational motion. The accelerometers detect a small change in velocity, and the radio signal reveals how the distance from Earth is changing. Each measurement is a reminder that the spacecraft does not exist only within a model. It is traveling through a real universe, where every force and every error can alter the journey slightly. The computer compares each new measurement with the prediction. If the two are close, it needs only to adjust the solution slightly. If the difference is larger, the system must consider whether the model is missing a force, the sensor is being disturbed, or the spacecraft has undergone a real change. It does not trust the prediction absolutely, but neither does it immediately discard the entire model because of a single unusual measurement. This idea lies at the heart of many sensor fusion methods, with the Kalman filter being one well-known example. Without going deeply into the mathematics, the system can be imagined as maintaining two things at once: a prediction of the spacecraft's state and an estimate of how certain that prediction is. Each sensor also comes with its own level of uncertainty, describing how accurate its measurements usually are, and under which conditions it is most vulnerable to noise. When a reliable sensor provides new data, the combined solution shifts more strongly toward that measurement. If the instrument is operating under poor conditions or is naturally noisy, its influence is reduced. The computer does not ask which sensor is always correct, because no such sensor exists. It asks which source of data is most likely to be closer to the truth at that particular moment. A camera may be highly accurate when the target is bright, clear, and near the center of the frame, but less reliable when sunlight spills into the lens. A gyroscope may record rapid motion better than a camera, but its drift gradually increases over time. Radio signals provide valuable information about distance and velocity, yet they can be affected when the transmission path passes close to the sunday. Reliability is therefore not fixed. It changes with the circumstances. This allows the sensors to check one another. The star tracker observes the sky and reveals the spacecraft's true orientation, allowing the computer to determine how far the gyroscope has begun to drift. During periods when the camera cannot see the stars, the gyroscope continues recording every small change so that the solution remains uninterrupted. One instrument provides an external reference, while the other preserves a memory of motion between observations. The sun sensor plays a simpler but extremely important role when the system encounters difficulty. If the computer is no longer certain of the spacecraft's orientation, it can locate the sun and place the vehicle into a safe state. The solar panels are kept facing the light, scientific instruments reduce their activity, and the antenna attempts to turn toward a region where communication with Earth may be possible. When the more complex solutions can no longer be trusted, a single direction of light may still help the spacecraft survive. Radio signals from Earth correct position and velocity errors that have accumulated over long periods. The atomic clock keeps every measurement aligned along the same timeline, preventing data from different sources from being assigned to the wrong moments. Pulsars provide a natural reference that depends less on ground stations, while optical cameras reveal where the spacecraft lies relative to the planet or asteroid ahead. None of these instruments creates the entire map, but together they compensate for one another's weaknesses. Cameras measure angles well but may struggle to determine distance while the target is still extremely far away. Radio signals measure range and line-of-sight velocity with great precision, but do not always describe sideways motion effectively. Inertial navigation operates continuously but gradually drifts, while the more independent pulsar method requires long observation periods to collect enough photons. This combination makes the system more resilient to individual failures. If one sensor temporarily loses data, the remaining instruments may still preserve a solution accurate enough for the spacecraft to continue operating. But this works only if the computer recognizes which sensor is experiencing a problem. An incorrect measurement assigned too much confidence can drive the complete solution away from reality, even faster than receiving no new measurement at all. An unexpected bright point in the star tracker's camera may not be a star. It could be created when a cosmic ray strikes the detector, leaving a mark that appears in only one frame. If the computer immediately treats it as a genuine landmark, it may calculate the wrong orientation. The system therefore checks whether the point appears repeatedly, matches the star catalog, and forms a reasonable pattern with the surrounding stars. A streak of light in the navigation camera can also be misleading. It may be the target planet, a star stretched by a slight vibration of the spacecraft, or merely an internal reflection within the lens. The computer does not simply locate a bright object and immediately alter the trajectory. It compares the object's shape, motion, and brightness across several frames to determine whether it behaves like the real target. A gyroscope may function well for many months and then develop a different bias as the temperature inside the spacecraft rises. An atomic clock may continue ticking steadily while remaining slightly separated from standard time because of a synchronization problem that occurred long ago. A sensor does not always stop working completely when it develops a fault. More dangerously, it may continue producing numbers that appear reasonable while drifting farther and farther from reality. To detect this, the system monitors the difference between predictions and measurements over time. A small discrepancy that appears randomly and then vanishes may be only noise. But if the same sensor repeatedly deviates in one direction, its error characteristics may be changing. The computer can then reduce the instrument's influence, switch to another source of data, or indicate that the spacecraft should enter a more cautious operating state. Rejecting an abnormal measurement can sometimes be more important than using it. If the camera suddenly reports that the planet has jumped to a completely different position within a few seconds, the system should not immediately rotate the spacecraft or fire its engines. A planet cannot move that way. So the problem is far more likely to lie in the image or the recognition process. The physical model becomes a barrier that prevents the spacecraft from reacting too strongly to an impossible signal. However, the system must not become too rigidly attached to the model. If several independent sensors all indicate that the trajectory differs from the prediction, the cause may be a real event that the model did not include. An engine burn may have produced a different amount of thrust than expected, or the spacecraft may be experiencing a small force acting over a long period. Autonomous navigation must be cautious enough not to trust a single measurement, yet flexible enough to change when the evidence becomes consistent. This autonomy becomes essential because distance prevents Earth from participating in every decision. Between Earth and Mars, the one-way signal travel time changes with the positions of the two planets and can reach about 22 minutes. An urgent message sent to Earth and followed by a response could require nearly 44 minutes just to complete the round trip, without including the time humans need to analyze the problem. During those 44 minutes, a lander may already have crossed the entire Martian atmosphere and reached the surface. A spacecraft passing near an asteroid may already have moved beyond its closest approach, while a dangerous object may have crossed the distance within which the engines could still avoid it. Humans on Earth continue to design the strategy and provide safety limits, but at the decisive moment, the onboard computer must read its sensors and act on its own. During landing, the camera may observe the surface, recognize craters and large boulders, and compare them with a stored map. Radar, or an altimeter, provides the distance to the ground, while the inertial system tracks the rate of descent and the spacecraft's tilt. The computer must combine all of this data within seconds, decide which region is safe, and adjust the engines before the remaining distance disappears. There is not enough time to transmit every frame to Earth and wait for a remote pilot to respond. Even so, autonomous navigation is not magic, nor does it mean the spacecraft understands the universe the way a human does. The computer works only with maps, sensors, physical models, and rules designed in advance. It can process thousands of measurements very quickly, but if it encounters a situation beyond every assumption, the solution can still be wrong. Processing speed cannot fully compensate for an incomplete map or a sensor providing false information. Autonomy, therefore, means more than knowing how to continue. A reliable system must also know when it should not continue. If the data becomes too contradictory, the position is no longer certain enough, or the camera cannot recognize the target, the safest choice may be to stop the maneuver. The spacecraft reduces its activity, conserves power, returns to a stable orientation, and waits for better observing conditions or guidance from Earth. Entering safe mode is not a sign of failure. It is like a person walking through fog who decides to stop rather than continue in an uncertain direction. When the system no longer knows clearly enough where it is, slowing down can protect the entire mission. A delay can often be recovered from, while an engine burn made in the wrong direction may sometimes be impossible to reverse. Engineers therefore design several layers of limits. The spacecraft may be allowed to make small adjustments on its own within a known range, while larger maneuvers may require additional confirmation. If a sensor reports a value outside physical limits, the data is rejected. If several systems lose reliability at the same time, safe mode is activated rather than allowing the computer to continue guessing with false confidence. An autonomous spacecraft does not need consciousness to find its way. It does not need to feel anxious when the data conflicts, nor does it need to understand the meaning of the planet ahead. It only needs to keep asking one very simple question. How different is my prediction from the new measurement? And is that difference reasonable based on what I know about the world? That question is repeated after every measurement. A prediction is made, new data appears, the uncertainty is updated, and the solution shifts slightly. Through millions of these cycles, the spacecraft maintains an understanding of its position, without ever assuming that understanding is perfect. It does not seek absolute certainty, but a solution reliable enough to support a safe decision. Within the solar system, Earth can still check the results from time to time. Ground stations measure the distance again, update planetary orbits, transmit new pulsar timing schedules, and help correct errors that have accumulated. The spacecraft may operate autonomously for hours or days, but behind it remains a network of people and antennas following the journey. An interstellar spacecraft will not always have that support. When distance is measured in light years, a question sent home may take years to arrive, and the reply may require several more years to return. By the time the guidance reaches the spacecraft, it may have crossed a large part of its journey, and the situation that caused the question may have changed completely. At that point, the ability to determine its own location is no longer a backup system. It becomes a requirement for the journey to continue. The spacecraft must carry its maps, clocks, models, and every method needed to check itself across many decades. Ahead, there will be no regular conversations with Earth, only a long path without landmarks between the stars. When the spacecraft is 1 light year from Earth, a signal sent home takes a full year to arrive. Even if the ground stations receive the question and respond immediately, the spacecraft must wait another year for the message to return. During those 2 years, it has continued traveling across a vast distance. Its instruments have grown older, and the situation that caused it to ask the question may no longer exist. Distance now separates the two places not only in space, but also in time. Within the solar system, communication delays are usually measured in minutes or hours. Earth can still track the trajectory, transmit new maps, and correct errors that have accumulated aboard the spacecraft. But on an interstellar journey, the delay is measured in years, and a complete exchange may last longer than many critical phases of the flight. Ground stations can remain valuable reference points, but they cannot serve as real-time pilots. Radio signals also weaken as they spread across an ever-expanding region of space. A message strong enough, while the spacecraft is still near the planets, may become fragile after traveling trillions of kilometers. The onboard antenna must be aimed with great precision, the transmitter must provide enough power, and receiving dishes on Earth must patiently gather every tiny trace of energy. No matter how far communication technology advances, the spacecraft must accept that there will be very long periods when it can rely only on itself. An interstellar spacecraft therefore cannot carry only fuel, engines, and scientific instruments. It must also carry a miniature version of the entire navigation system once distributed among Earth, satellites, and observatories. Its memory must contain star catalogs, the relative positions of distant radio sources, pulsar timing models, maps of celestial motion, and rules for detecting when a measurement begins to behave abnormally. A star catalog cannot be only a fixed image of the sky as it appeared on the day of departure. Stars have their own motions through the galaxy, even though those changes are extremely slow to human eyes. Over several decades, many constellations will still retain nearly the same shapes, but nearby stars may shift enough that a precise navigation system must account for them. The onboard map must therefore describe not only where each star once appeared, but also how its position is expected to change in the future. The solar system is not standing still within the galaxy. The Sun and its planets are moving around the center of the Milky Way, carrying the entire starting point of the journey with them. When the spacecraft looks back after many years, Earth is no longer where it was when the spacecraft departed, and the Sun has also continued along its galactic orbit. There is no motionless grid stretched across space upon which everything travels. The map and the traveler are both drifting through the same moving universe. Pulsars are not clocks that remain completely unchanged. They gradually lose rotational energy, so their periods usually slow by a very small amount over time, while some may undergo sudden changes in rotation rate. Pulse timing models must be updated and projected far enough into the future for the spacecraft to continue recognizing the signals after many years of silence. If the onboard pulse schedule becomes too old, the difference between the real rhythm and the prediction may be mistaken for a positional error. The spacecraft's atomic clock must also preserve its stability over a period far longer than most missions today. It does more than count the seconds that have passed. It helps connect every measurement to the correct moment in the journey. As the spacecraft's velocity increases, or it passes through regions with different gravitational conditions, time aboard the spacecraft and time on Earth will no longer pass in exactly the same way. When high precision is required, relativistic corrections must be included so that widely separated clocks can still be compared correctly. Space is therefore not like a motionless sheet of graph paper where the spacecraft simply reads its coordinates and continues along a straight line. Natural landmarks are moving. The rhythms of signal sources are changing, and even the measurement of time is affected by velocity and gravity. Interstellar navigation is not only about knowing where the spacecraft is, but also about understanding how the entire reference frame around it is changing. Between observations, the inertial navigation system continues preserving a memory of motion. Gyroscopes record every rotation, while accelerometers measure extremely small changes in velocity. But after many years, no internal sensor can completely avoid drift. The spacecraft must therefore periodically open its eyes to the outside, observe stars, pulsars, or extremely distant radio sources, and use them to correct its own memory. Quasars can serve as nearly fixed reference points in the sky, because they lie at immense distances. The spacecraft's movement across several light-years changes the viewing direction toward these sources only slightly, allowing them to maintain a stable reference frame. Pulsars provide natural timing rhythms, while nearby stars can produce more noticeable parallax as the spacecraft changes position. Each type of source answers a different part of the navigation problem. Parallax can be understood as the apparent shift of a nearby object when the observer changes position. Hold a finger in front of your face and close one eye, then the other, and the finger appears to move against the background. A spacecraft traveling across a vast distance can likewise observe nearby stars shifting relative to more distant sources. That small displacement contains information about where the spacecraft is located in space. As the spacecraft approaches its destination star, the target itself gradually becomes a more important landmark. At first, it is only a point of light in a catalog, almost indistinguishable from other stars, apart from its name and coordinates. Over the years, its apparent brightness, position, and motion against the background sky will change. Any planets orbiting the star, if they can be observed, will provide additional clues as the spacecraft transitions from navigation between stars to navigation within an unfamiliar planetary system. However, there is no complete interstellar GPS system ready to be installed aboard a spacecraft and placed into service. Some components have already been demonstrated, including star trackers, radio navigation, space-based atomic clocks, and experimental positioning with X-ray pulsars. Other methods remain under study, especially as requirements expand from missions lasting several months within the solar system to journeys spanning many decades between the stars. Interstellar travel will require a combination of existing technologies and solutions that have never been tested on a practical scale. The greatest difference may not lie in a new sensor, but in the autonomy of the entire system. The spacecraft must determine for itself which sensors are drifting, which maps have become outdated, and which measurements no longer agree with the model. It must know when to correct its trajectory, when to wait for more data, and when to enter a safe state. Those decisions cannot be delayed for years simply because an answer from Earth has not yet arrived. A very small change in velocity in interstellar space can accumulate over decades and shift the destination by an enormous distance. The spacecraft must therefore make gentle corrections early, while enough time remains for a small push to gradually reshape the trajectory. Every engine burn introduces a new error that must be measured again. The journey is not a straight line drawn once, but a sequence of predictions, observations, and corrections repeated across many years. The star tracker tells the spacecraft which way its body is facing. The sun sensor helps the solar panels find the light again and keeps the spacecraft alive when more complex systems encounter difficulties. Gyroscopes preserve the memory of motion through periods of darkness, while accelerometers record the changes produced by engines and the surrounding environment. Each instrument understands only a small part of the journey, but that small part becomes essential when placed beside all the others. Radio signals from Earth measure distance and velocity while the communication link remains usable. Quasars help establish direction against the background sky, while the atomic clock turns signal travel time into an invisible ruler. Pulsars provide natural timing standards distributed throughout the galaxy, while optical cameras observe the destination and narrow the uncertainty as the spacecraft draws closer. No single source of data can complete the map on its own, but together they can make it reliable enough for the spacecraft to continue. The onboard computer combines all of these measurements into a solution that is never absolutely perfect. It understands that its position may lie somewhere within a certain region, that its velocity may differ by a small amount, and that time still carries uncertainty. Rather than hiding those limitations, the system includes them in every decision. It does not need to know its position with infinite precision. It only needs to know it clearly enough for the next correction to bring the journey closer to its destination. After many years, the light from Earth will grow so faint that home becomes only a small point among countless stars. The signals arriving from there will describe a planet in the past, because every message has taken years to cross the distance. The spacecraft will send back replies that their recipients can hear only in the future. The two sides will remain connected, but they will no longer share the same moment in the conversation. Within that silence, the spacecraft finds no path waiting to be followed. There are no glowing lines stretching from the sun to the destination star, no signs marking where to turn, and no satellite network surrounding the entire galaxy. The path appears only inside the computer after each measurement, then changes when a new signal arrives. It is a temporary structure assembled from light, motion, and time. The spacecraft observes stars through light that left them many years before. It counts X-ray photons too sparse for the human eye to recognize as a rhythm. It keeps time through the oscillations of atoms, remembers every rotation through gyroscopes, and listens for radio echoes fading from its distant home. Every method is imperfect, yet those imperfections can be used to check one another. In the darkness, where there is no horizon, no absolute up or down, and no GPS, the spacecraft can still know where it is going. Not because the universe has drawn a clear map in advance, nor because a perfect compass exists to point unerringly along the way. It finds its path by reading the traces the universe leaves behind in the travel time of light, the shifting angles of the stars, and the rotational rhythms of dead stellar cores. A traveler between the stars can never stand outside the universe and see the entire path at once. They receive only small signs, then use those signs to construct a solution reliable enough for the next step. Perhaps this is how every journey of discovery has always unfolded, not through absolute certainty, but through the patience to measure again, correct the course, and continue moving forward. Behind the spacecraft, Earth continues orbiting the sun, carrying its oceans, cities, and antennas waiting for a signal from far away. Ahead, the destination star slowly grows brighter with each passing year, changing from a point in a catalog into a place that can be reached. Between them, the spacecraft quietly constructs its own path, not from visible landmarks, but from light, motion, and time.